we can do a reset on this. You want to try a
no,
reset?
No, I think we need to change the resolution.
Otherwise, get a Mac. Okay, so I think we... you're still trying things.
Okay, I'll just change the resolution.
So Petri has been working, or has been supervised by Mari, and that's when they did a lot of work on convection. And over the last few years, he has also been doing direct dynamo simulations. And he will be now, however, talking about something without magnetic fields altogether. No magnetic fields, but there's an important mean field transport coefficient effect, which is called the lambda effect. And in the ADS, they sometimes call it the A effect, because they don't know how to make a lambda. So, Petri, please.
Thank you. So, I will be talking about something that we have been kind of working on for a while, which is kind of a side product of our dynamo simulations in shearing boxes. And this is related to angular momentum transfer by convection, and in particular when we have a large-scale shear flow. And this was actually pointed out to us by Ramesh Narayan, who was here visiting in the summer of 2008. We were writing a paper on the dynamo side of things, and he was asking, well, what does the Reynolds stress look like in these simulations? And that was the first time that we actually took a look at that and realized that it's in contradiction to results that have been published on that subject previously. And that kind of triggered us to do more research on this field. And this is mostly related then to the accretion disks and what convection could do in an accretion disk in terms of angular momentum transport. First, I will talk a bit about the basics of turbulent angular momentum transport on a very general level, and then I will show you some results about turbulent viscosity and indeed the lambda effect. Yes?
Let me ask a general question, maybe a little bit stupid. What's the source of heating in accretion system? Because we haven't something similar to radiation core and thermonuclear.
You mean that if we want to have convection in an accretion disk?
Just for wire, from wood, not from
well,
solid.
we don't really comment on that. We just assume that there is
somehow,
and that produces convection.
Yeah, but the idea is, of course, that the disk is heated, like all disks are always heated, by the viscous heat.
Viscous.
So it's some kind of a bootstrap thing. If this whole thing was supposed to be self, no, of course it's not. We know that
At
now.
least not in our simulations.
But it was, of course, not evident when it was first addressed. But he's talking about a general problem which was addressed in '96, and there's a mistake in that treatment, as you will find out.
Well, actually, their results are correct, but they are based on a limited number of data, which is the problem. And okay, but this is the last part of the talk. So, just some very general considerations. First of all, if we consider a star, and we are in spherical coordinates, and for simplicity, we assume that we have an axisymmetric case. Then the angular momentum conservation equation is very simple, or it's deceivingly simple. You just have these three terms. You have the angular momentum itself. S here is what's called the lever arm, or the distance from the rotation axis, r times sine theta. And then you have a divergence of flux. First of all, we have the meridional flow here, which is which can occur because of various different reasons, and this is one of the hidden aspects here. And then we have the turbulent transport, which is due to the Reynolds stress, which is just the correlation between fluctuating velocity components. And the reason why I say that this is a bit deceivingly simple, this equation, is that well, here you would say that okay, there's only velocities here, and what about the effect of convection and heat fluxes? And they basically all then crop up in the meridional flow. If we have a baroclinic term in our equations, this will drive the meridional flow, which will then ultimately change our rotation. So it's not only the Reynolds stress which solely describes how angular momentum is distributed. But in this talk we will just concentrate on the Reynolds stresses in different systems, and one very early parameterization. Then we want to express the Reynolds stress in terms of large-scale velocities, and one of the simplest assumptions is to use what is called the Usinesque ansatz, where we just relate our Reynolds stress to the turbulent viscosity and gradients of the large-scale flow. And of course, if you want to be rigorous, this is not entirely correct. You have to have extra terms. But for the time being, let's just consider this equation, very simple equation. And then we immediately, well, not immediately, we have to look at the sun for a while. And then we end up with a problem, because if you look at what we call now the horizontal stress, so this is the correlation of the latitudinal and then the azimuthal velocities. In spherical coordinates, we get this sort of expression for that. Or do we? I think the unit is wrong.
Yes,
looks okay.
You should add R.
Yes,
R.
that's right, and R is missing here.
You divide by R.
Yes.
No, but you multiply again. I thought.
No,
Well, it should be
in
velocity.
order to
It
get
should be velocity gradient.
It should be velocity squared.
Yeah, but that's okay. It's okay.
Oh yeah, of course, right.
Okay.
Oh, guys.
Okay.
Yes.
Okay, so
Yes.
in the sun, of course, if we look at the northern hemisphere, we know that sign is positive, and then observations of surface tracers tell us that also the latitudinal gradient of omega is positive. But then, if we look at sunspot statistics, then we can also derive independently the Reynolds stress. And it's found out already quite a while back that this is also a positive number of the order of 10 to 3 meters squared per second squared. And if we just then put all of these guys into this equation, we would come to the conclusion that our turbulent diffusion should be negative, which is something that we don't really believe that is correct. That we shouldn't have negative diffusion. So the way out of this is to postulate this is not the full picture, but that we have some additional non-diffusive contribution to the stress, which I always refer to as the lambda effect here, which is not the only thing, but maybe we come back to this later on. So the lambda effect, then I have put here to distinguish that this is the Reynolds stress due to the rotation. So we have another tensor, and then which is proportional to the rotation rate of our system. And this lambda effect occurs in turbulence, anisotropic rotating turbulence. And there is quite a bit of numerical simulations where this has been studied with convection simulations and also with forced turbulence runs. And this is actually kind of a reverse succession of things. That first people did convection simulations where you have all sorts of other effects that could come into play. For example, it's difficult to We have mean flows which could also produce diffusive contributions and stuff like that. And then this last paper here we did with Axel, we had just homogeneous but anisotropic turbulence. And we added flotation with that, and then there shouldn't be any contribution from turbulent viscosity in that case. And here you see the results for different components, off-diagonal components of the Reynolds stress, which is not that informative. So here is now the horizontal stress that was also observed or inferred from the observations of sunspots. We see that it's positive, and it's 0. This is now the pole, and this is the equator. This is now the latitude, not the co-latitude here. And the maximum is around 30 degrees from the equator. And then this is the other components which is important for the differential rotation. This is now the vertical, essentially the vertical flux of angular momentum. And we see that it's always negative in our runs here. And okay, so we know that there is a lambda effect, but we also know that there is turbulent viscosity. And but so far there hasn't been really much effort to derive or compute turbulent viscosity from this sort of convection simulations. At least to me, in most of these, or all of these cases, where rotation is imposed, then the Reynolds stress is taken to represent only the lambda effect. Probably for simplicity.
He knows that.
Yes, I mean,
So
the thing here is that if you have this Cartesian box convection simulation, then you have your rotation vector, and if this is inclined with respect to your gravity vector, then you will get also large-scale velocities, which would give rise to the diffusive contributions of turbulent viscosity.
Okay. Maybe
So in a sense there is no justification of dropping turbulent viscosity in this analysis.
Yeah.
But it's very difficult to distinguish the contributions.
Okay.
You have one number which is proportional to two contributions.
So if considering turbulent viscosity, like turbulent diffusivity, for instance, as a property of the turbulent flow, then this property should, of course, exist.
Yes.
But it's not detected by the specific mean flow you employ.
Yes.
Okay.
So that's why we need Matthias to finish his test field method, of course.
Yes.
For the good old test flow method, yeah.
Okay, so
Very fun.
what we then want to do, our model is one that has been presented here many times probably. So we have a Cartesian box where we have ideal gas, which is heated from below, and then we arrange our thermal conductivity so that we have a convectively unstable layer in between two stable layers, below and above. And above we also apply cooling, which keeps the temperature constant. And then we have a bunch of different dimensionless numbers here, which describe our system, and then we have a very simple shear profile, which depends on x, and then we have our rotation, which is now always in the vertical direction, and for the accretion disk configurations, then we have the parameter q, which describes the rotation profile in the disk. But okay, I will come back to this later on. And I have a small animation here for a typical run with shear and rotation, although this is a short. So this is the highest Reynolds number that we have applied so far.
This was hyper Viscosity?
No, this is with regular viscosity. Yes.
Everything-
That's a 1,000 cube runner.
Yeah? Oh.
Yeah. So that was actually done to test the remeshing thing with convection,
Okay.
which
Which works.
doesn't still work perfectly.
Somebody was saying doesn't work, yeah?
Yeah.
Who was it?
You were saying maybe. it
Yeah,
doesn't
I was saying that.
work. Yes, I see.
Yes, it does work, but not. It works only with if you increase the number of processors in the Z direction. If you increase processor number in the Y direction, then it doesn't work.
So Simon needs to
Simon
check
is there,
that.
but he's
Where's Simon? You listen?
No, I just missed the last part.
No, it was about the remeshing we
Oh,
talked
yes,
about.
yes. Actually, we're talking about this
Yeah.
on Monday.
Oh, yeah. That's right.
But the thing is that I cannot imagine that one direction gets preferred at the remeshing because it's perfectly symmetric. And I think when we were going through this with Niels, we also saw that it's perfectly symmetric.
Hmm.
I think
Yeah,
the
I mean-
problem is not a part of the code.
Hmm.
I'm not sure.
Maybe it's a part of the user. Okay, anyway.
Computer, user, and code.
User error. Replace user.
User error, not user property.
Okay, so now this might be a bit controversial. It's Nathan, the next step that we do. So now we start with the simulation where we have no rotation and only shear. And we assume that this imposed shear is the only large-scale flow.
Maybe you need half, no? Two, two in
here.
in first line, in the end. Two new
here.
TS.
Yes.
No? Should be two, right?
Yeah.
No.
One?
One.
No, that's only one of the two derivatives.
Because
Sure,
it's
you get
half of
But
this
the
here.
S is defined as 7.5.
Oh,
Is it?
Yeah.
according to
I mean,
definition.
normally,
it is-
Oh no, S. Yes, S is. Sorry, that's correct then. S is not the shear tensor. S is just the.
No,
shear
it's,
parameter.
S is not shear tensor, it's okay. But shear,
Yeah,
S is just.
definition.
S is just the derivative. Yes,
But never mind.
the coefficient.
So S is
Yes.
Yes, in this
right.
context. But you know, it's really S. If after calculation,
Yeah.
it should be.
It's the strain tensor. I mean, but then times 2. Yes.
You mean we should replace S by some other number or other letter?
I mean, it's a different character. One is sans serif, so it's not a sans serif one.
Yeah.
Yeah, this is higher
Small
mathematics.
correction. Yeah.
Yeah, typographics.
Okay, and then what we also assume is that all mean quantities are then functions of Z only. So here now is the Z coordinate and the convectively unstable layer is between these two vertical lines here.
What's the boundary condition? Periodic? Oh,
In the horizontal direction, it's
vertical.
vertical is stress-free.
Stress-free.
Both?
Both. And then we just use this equation. We get our ground stress from the simulation, then we know S, and we can compute the turbulent viscosity. Okay, here, there's a T missing here. This is the turbulent viscosity, and then it's divided by an estimate μ0. And we see that, well, at least it's positive, which is a good sign. And what might seem alarming here is that if we look at this number, which is essentially a straw hole number, we see that it's something like 15 in this case, which is pretty high. And we see that when we increase the shear, then we decrease our straw hole number again by a factor of something which is not very much. And okay, maybe that's enough for that. So we get.
I think we understand why this is so large. Because
Yeah, actually, on the next slide I have something more on this. Yes. So then if we just naively take our Navier-Stokes equations and derive from that a time derivative of our Reynolds stress, so we get a term which is like that, ux squared, well, this is one of the diagonal components of the Reynolds stress, plus other terms, and then we do the usual trick, we drop this guy, and then the other terms are just the stress divided by tau, and we get this sort of equation for our Reynolds stress. And then here on the graph we compare the, this is now the stress from the simulation itself divided by the volume average of URMS, just to get a dimensionless number. And then we have this expression overplotted, and now I have tuned the tau so that these curves go approximately on top of each other. And tau is now such that the straw hole number, which is defined like that, is 4, which is still fairly high. Well, for an astronomer, of course, this is of the order of unity, so unity is what we expect.
Tau is the coordination time of turbulence, right?
Yes, and we are using it as a free parameter in this analysis.
So it's not.
So it's not, yes.
But in principle, you could just use numbers from simulation.
Yeah, in principle, we should be able to compute the correlation time directly from the flow simulation.
So if I define tau by just URMS and KF, then how would that compare? Well, that's one.
So then straw hole number would be 1, and this would be 4 times less, this dashed curve here.
But we never checked that for this convection flow. We only checked that for force turbulence. I think.
Yeah, so what is KF? You don't have a KF.
Yeah, that's the other problem.
Yeah, KF is, that's of course a problem. So KF is just a 2 pi divided by the D, and D is now the depth of our convection zone.
So we believe now that 1 over kf should be replaced by 1 over kf plus h, and h is the scale height. And then if there's rotation, there's a few more, there's other additions to that.
Yes.
It's the Rhines scale. So I think that would alleviate this problem with the large numbers, and maybe also with this number 4 here.
Yeah, yeah. And actually here, tau is just one number. Probably also depends on depth.
Yes.
So, but we haven't really done anything as sophisticated as that. Actually, this was done this morning for the first time. So.
But isn't that formula pretty strange? Because it says if the shear goes to 0, the stress goes to 0.
Yeah,
Yes.
but that's the off. That's the
That's
off.
off diagonal.
Okay, yeah, you're right. It's not the coefficient.
Yes.
The coefficient is kept.
Okay. So then, if we add rotation, then we also have not only our diffusive coefficient, diffusive contribution, but also a non-diffusive contribution. And then, using a similar dirty trick, we can get the lowest order contribution to the stress due to the rotation. And now it's, well, this is basically a Coriolis number here in front, and then we have the difference between the horizontal velocities, essentially. And why do I say that this is lambda effect due to shear-induced anisotropy? The thing is that if you remove shear from this system and you have rotation parallel or anti-parallel to gravity, then the turbulence will be, there will be no difference between x and y directions of the flow. And then the lambda effect would vanish. And then of course the problem is that if we have both of these in our simulation, it's not very easy to distinguish the different contributions. So what we do is that we determine turbulent viscosity from a non-rotating one, and then do different runs where we add rotation and use our turbulent diffusion from the non-rotating run and then determine our lambda effects. And this is done here on the left. This is a very recent plot. It's about 2 hours old. And what we see that we have a constant shear in all of these calculations, and then we determine our normalized lambda effect from this equation, and then we have rotation increasing from a very low value to higher values. And then we get this profile for our lambda effects, and it seems that this coefficient is decreasing as a function of rotation. So that when rotation is very weak, this coefficient is very large.
So the shear is constant, yeah?
The shear is constant. And of course, here we have, this is fairly rapid rotation, correlation number of 1. So it's not really entirely clear that we can still take the turbulent viscosity from a non-rotating run, because turbulent viscosity is probably also affected by rotation. So
Decrease.
yeah, probably it will decrease.
So the effect will be increased.
But only probably only by 30%, I think.
Yeah. So
Do you have do you know the power law with which lambda is being quenched by omega?
no,
maybe
no,
one?
this is. I just was able to make this plot before the talks.
Mm-hmm.
I'm afraid I don't have that yet, but that's definitely something very interesting to put in the paper ultimately at least. And what I have done here on the right is just to take this rotational contribution to the stress, which is also computed now from here, as the difference between the total stress and the diffusive stress. And then I compare it with this our analytical results for the lowest order contribution to the lambda effects. And again, I have used tau here as a free parameter, and then tuned it so that we get a fit, and actually we get a very nice fit here. But the Strawhall number is now 20. So I don't know what to make of that.
But that's with rotation.
Yeah, that's with slow rotation. So this is the lambda effects, or the non-diffusive contribution to the stress we see. So I'm not quite sure what to think of this, because when I increase rotation, then I can make similar fits, and then usually the Strawhall number is less. Yes.
If you impose just shear without rotation,
Yes.
can you find non-diffusive or non-viscous contribution in this approach?
We don't have any rotation.
Yes, just shear.
Then, okay, then we interpreted that the stress is diffusive.
No, it's not. It's maybe not, because at least according to our calculation, we've got additional contribution non-diffusive, which generate vortex dynamo similar to shear current mechanics. So maybe it is solving a few puzzles, because if omega tends to 0, you should find something infinite. But if you've got contribution which is not proportional to omega, it could be possible, huh? Maybe you should check it.
Mm-hmm.
Mm-hmm. Yeah, I mean, but we do see that when we decrease rotation, then this
Yes. Nevertheless, you will find something
yes.
which proportional to shear.
Oh, wait, I mean, I think you would be talking about another component of the new tensor. I mean, he's talking about...
Okay, you're right. Not
Okay.
not
Okay,
diagonal
now I understand.
component.
Yes.
Right.
Okay, that we haven't really looked into.
Yeah,
Not in this case.
Yeah, and this probably would be a nice exercise for the test flow method. Again,
It's exercising all the time.
yes. Okay, so maybe I continue. Okay, there's one more thing. That's it is possible in this case that the imposed shear is not the only large-scale flow. And then our assumptions that our stress would be just a function of Z would no longer be correct. And this is because we do sometimes see that when we have shear, that there are other large-scale velocity components, which also depend on X. And those components we have not taken into account in any of these analyses yet. But that's something that we really need to look into. And okay, then I will go to the accretion disk consideration. This is now in a paper of Stone and Balbus. They did similar things, not with the same setup, but some different stratification and gravity, but in principle the same thing, that they have convection happening in shearing box calculation, and then they compute, this is now the Rxy component to the stress. So what they find is that the stress is very small. Now this is in terms of a Shakura-Shuyaev viscosity parameter, and which is essentially the stress divided by the pressure. And what is peculiar about this, or what's not good for accretion disks, if you have convection there or any kind of turbulence, you would want to transport the angular momentum out of the system so that your gas can accrete onto the central object. But the sign of this stress indicates that convective angular momentum transport actually goes inward, not outward. And okay, here I have these Q parameters. Okay, so Q is just describing how the rotation profile looks like, and in our system this is just the ratio of S and omega, and Q equal to 1.5 would be a Keplerian case, so an accretion disk around a black hole, for example, or around a young star. So this looks alarming, but it's alarming also in another sense, that if you just have a single data point and then you draw your conclusions from that. This is now from another paper by Workman and Armitage, where they did, this is now a forced turbulence run in a Keplerian rotation profile. Forced turbulence, and that's a homogeneous system. And then they run this for a long time, and this is now the stress divided by the gas pressure, and they see fluctuations around 0. So they have a very small value in this particular case. And from this point, they draw the conclusion that hydrodynamic forcing or hydrodynamic turbulence alone cannot produce any stresses. From this one point. And we did something similar with a student of ours, and we had a very similar system, just forced turbulence in shearing and rotating domain, and then we vary here the Coriolis number, or how strong shear and rotation are. Then we see that for slow rotation, the diamonds here are now the simulations. Then we see that first it's positive, then it changes sign, then it's negative, and then it probably goes to 0 when you have rapid enough rotation. And actually it was not this paper, but another paper where we quoted this one, and we put the paper on the archive, and then the first author here contacted us, and he was totally dismayed, because they had done only 1 point, and then they draw very drastic conclusions from that. And this is a bit similar to the case of Stone and Balbus. So their case was also with the rapid rotation run. But if you start from a very weak rotation, and this is now with the Keplerian shear, first the stress is positive all over the place. And only if you increase rotation enough above Coriolis number 1, then you start to see that it changes sign and it's negative.
Yeah, seriously, maybe need to look at that?
What?
Because you just look at the system, you know that your epicyclic frequency is going to matter hugely.
Yeah.
Your correlation time to the epicyclic frequency is going to determine everything.
Right.
And
See-
that's sort of very, very basic.
So what are you saying?
The epicyclic frequency
Uh-huh.
to the correlation time. Imagine like if you give something a little bit of angular momentum extra, it'll start by moving out, and then it'll move back in. And your correlation time determines whether you dump your angular momentum when you're further out or further in. And correlation, and I think, depending how you're finding Coriolis number 1 is about where you'll dump about when you get back to where you started.
It's true. True, because if you got some fast rotation, of course your correlation time will be controlled by this
Yes.
fast rotation. So for every parameter goes over twice, normally, maximum.
Yeah. And okay, this was the point that we started to look into this whole business in the first place. That because this paper of Stone and Baltus has been quite influential in saying that, or that many people call it that convection cannot be the angular momentum transport method in accretion disks.
That's not, I think, the main reason why people think that convection can't.
Well, another reason is,
No,
of
there's
course,
the
that
energy
it's hard to
balance.
get convection going in.
No, there's also just the net energy balance is brutally ugly. It's not brutally ugly. The energy released by, if you just take an energy consumption of v squared divided by tau, and energy release from the, an energy consumption of the turbulence of v squared over tau, and energy release of, for some reason I can never do this one in my head, but due to the infall was induced, you're basically going to find yourself with a under budget. You can't release enough energy from the induced accretion flow to power anything, unless you manage to get something extremely efficient.
But I mean, if you calculate a model of the accretion disk, then of course it's part of the balance that you have to put in.
If your energy
M dot, of course,
if your energy source is m dot,
yes.
then m dot can't come from turbulence powered by m dot, because turbulence is inefficient.
Oh, you're talking about the convection, or
And basically any hydrodynamical turbulence.
as opposed to
Maybe
MHD.
you can get a really incredibly efficient.
Mm.
I think basically they just caps out. You just sort of like the perfect energy to torque conversion nets you neutral. I think. I don't really remember this that well. That's the main reason why.
Yeah, I think that sounds probably okay. Yeah, good.
Yeah.
I mean,
Okay. Yeah. I just have one figure that I shouldn't really show because it's so crap.
It's going to need explanation.
yeah, explain what is that.
There's just 6 different simulations with 6 different rotation rates. So 0.04 Coriolis number, it should be 0.08, 2.4, about 1, about 2.5. And you see the difference in the structure of convection. We have very large cells here, and as we increase rotation, then we see that rapid rotation, everything is aligned with our shear form.
But is it a question of scale? I mean, what happens if I take, for example, the one which is 0.5 and I stretch it?
You mean this one?
Yeah, let's say I take it and I stretch it. Do I measure the same power that I get on the other? Can I one of the low rotation.
I mean, you have to squash it. You have to somehow squash the whole thing in
Yes,
X,
and
right?
I just, for example, compress the high rotation rate and remap it to the low rotation rate.
Feeling that you've got something similar to cloud streets for fast rotation, am I right?
Closed what?
Cloud streets. It is
Cloud Street.
a system
Yes.
of clouds. It's similar,
Yeah.
it's elongated.
Contrails, yeah? Contrails, you mean?
No, it's named cloud streets.
From,
Roads.
from an aircraft, you mean?
From
No.
aircraft. Not
Yeah.
only. You
Not
can
only.
absorb from
Control.
ground.
Just from mean flow.
Mean flow.
You
This
don't see
mean
clouds
flow you
that get
absorb.
sheared
Yes,
out.
yes,
Oh, I see what you mean.
So you start from cells for low Coriolis parameter and
Yeah.
drive to something similar to cloud streets and for large Coriolis parameter.
Yes,
Mhm.
that's right. But I'm
Yeah.
not sure if you can just take this and stretch it to get that.
I mean, by the way, there's a...
It's not strange. It's just more or less. It's not so how to say trivial business because I'm pretty sure that you produce thermal flux which perpendicular to plane rotation and gravity. It is new.
So regarding Nicolas' question, when you can actually check this easily because we have a module called PC_unshear. So you just run this with a negative shear element, of course, so to make it shearing. And that one then you maybe
No,
enter.
I don't know. I mean, if it's a scale-free problem in the sense that you can find a way of getting one simulation and extrapolating to all
Yeah.
possible cases, or if it's really there is a difference when you are.
I think there is a
Not,
real difference, but
Yeah. So
there may be some approximate resemblance nevertheless, of
Yeah.
course. Okay.
yeah, actually, this was the last slide that I had.
Could you answer?
So short, yes, maybe, yes. go ahead.
Short question. What's the plane of rotation and gravity in this picture?
Rotation and gravity. Rotation vector is like this,
Yeah.
going pointing upwards.
And gravity is
Gravity is pointing downwards.
downward. So it's okay. So it's just parallel. You mean?
Yes, or anti-parallel.
Does your Mach number change below this?
Mach number. Mach number is, well, it's basically, it doesn't change by a lot, less than a factor of 2. It's always of the around of 0.1.
Differential rotation in what difference in velocity in what direction?
Well, it depends on x. So this is x.
And this is X.
So we have flow going
Flow.
here and then
Mhm.
out.
So it's basically in the direction of velocity, this direction of this cloud street-like
Yeah.
structures.
Yes, that's right.
It's very similar.
Yeah.
Yeah.
Yeah, I think we once I did an average of this,
Yeah.
and I showed it to you when you were in.
But
Looking at
today
this
it's
and
much
we-
more obvious.
Yes.
The structure.
Yeah, I mean that was a much less, or the shear was smaller in that case, but here it could be clearer.
Interesting. Because one of the results, as I remember, what's important in this situation is you've got combination of shear and thermal flux. If you've got shear and thermal flux, you've got additional flux in direction of velocity. And this additional flux produces, I think, according to our at least calculation of the structure.
You mean in the direction of the shear, I mean?
No. Shear it says, no, production of shear and product of shear and gravity gives you additional direction.
Yeah.
Yeah, and this direction maybe will be the direction, more or less.
I
It is additional
epsilon
flux.
IJK, W, J, and
Yeah,
gradient.
something, right.
Yeah, right. Indeed.
And this is, of course, additional co-contour wind flux. It's known in.
Oh, but that was in the zone direction. Anyway,
Never mind in what, maybe opposite. It depends, sign of your shear.
perpendicular to the gradient, at least.
It's not parallel to gradient of temperature. It's
Oh, I see.
just in perpendicular. something omega cross F. It is more or less known feature.
This is 0 here, no?
Maybe it's zero in this situation, but if you've got somehow similar to inclination, it's the same property.
So you could maybe show us again this plot with the curve, the last previous one or something. Yeah, no, the other one. Before. And then to the right. To the right of the workman picture, perhaps. Next one. Yes, this one. So your simulations were, I mean, these were all your simulations?
Yes.
And are you saying this simulation was essentially here?
That simulation is somewhere here.
I see. Yes, right. And then the stone and valvus one was maybe here.
Yeah, it's around here. Yes.
But it's wrong.
No, I
Should be
mean
less than one. No, wrong in physical sense.
I mean, it's right in the sense that it is negative, but it's not true to say that it's always negative.
Yes, of course.
That's
And realistic situation should be also even less.
I mean, the people were really surprised about this result back then. Some people thought it should be positive, and they of course got this result, and some people thought maybe there's something wrong with the simulation. But everything is alright, and it's just that part of the story only. Here's the full part of the story.
But who knows? Maybe system somehow understand what level of tau naught should be choose.
It still doesn't mean that it's relevant for accretion disks, of course, perhaps, because as Alex was saying, it's very inefficient, of course, and you cannot bootstrap the disk from its own heat somehow, or cannot heat its from your own friction.
Convection should produce the heat that drives convection.
Yeah, it's like you're sitting in your room and you're jumping all the time to make yourself warm. Of course, you're somehow consuming energy, but you're heating at least the whole room. So in some sense, you would think you have a perpetuum mobile, but of course you don't, because you have to eat in the meantime.
Not only jump.
That's what's missing.
I will note that protoplanetary disks uniquely, and fairly uniquely, have their temperature determined by irradiation.
Yeah, exactly.
So they are unique in the accretion disk.
Yeah. So the heat comes actually from above, rather than from below, not from friction.
But in this situation, difficult to believe that we've got convection.
Well, your heat goes into the dust disk, and convection presumably happens in the gas disk. So it is conceivable, just
But
that there is convection.
so you mean
Sure, gas-
if
for gas-
infrared radiation penetrate via gas
If your-
and hit you?
If your gas is
there?
almost monoatomic or diatomic, it'll have very low opacities. Your dust has huge opacities. You get a very
get an
brittle
image.
dust.
But
I find it's not very believable.
okay, you mean infrared radiation and the
Any radiation, gas is very low opacity.
so that is enough transparency. You mean?
Gas is very transparent compared to dust, and there isn't that much mass in these gases. So the gas is very transparent, and you're mainly heating through the dust. But that requires you to have highly settled dust in a turbulent disk, which is not easy.
Why? If you got minimum temperature instead of maximum, it's very easy.
Yes.
And of course,
but that's
of course your disk is also cooling by the dust as well. So
Yes, but maybe it's some kind of instability. A combination of thermal thermal diffusion and cooling due to radiation losses. And many years I thought about it.
wow. You mean because of the temperature minimum accumulation?
Yeah, you
That's-
accumulate additional
wow.
particles and it increase until they arrive to depth, optical depth equal 1. And you stop this process.
Oh, this
So
could be-
thick disk, which accumulate particles,
Sorry,
it's
yeah.
very, how to say, interesting
Yeah.
scenario.
Okay, good. So maybe you should get back to work. So if there are no further questions, then let's thank Petri again.